Hello and welcome to today's lecture on static CMOS circuits. This is the first lecture on this topic, and in two lectures I shall cover different aspects of static CMOS circuits. In the last four lectures I have discussed about various aspects of MOS inverters, how different types of inverters can be realized, their characteristics, static, dynamic and so on. And as I mentioned earlier, we are following bottom up approach. So, starting with MOS transistor, we have discussed MOS inverters. Now, we are discussing more complex circuits realized using static CMOS circuits, static CMOS technology. Here is the agenda after a brief introduction, which will also include some recap of the previous lectures. I shall discuss about CMOS multi input gates. We shall see how multi input gates can be realized by extending the idea of MOS inverters. Then we shall discuss transfer characteristics of NAND and NOR gates, and after that we shall discuss switching characteristics of NAND and NOR gates, and finally we shall compare the characteristics of NAND and NOR gates realized using static CMOS technology. Here is the brief recap about what we discussed in my last four lectures. We have discussed about different types of inverters that can be realized by using MOS technology. We have seen pull down device is always a NMOS transistor, but pull up device can vary. It can be a passive resistor or it can be some active devices, particularly NMOS depletion transistor, NMOS enhancement transistor, pseudo NMOS circuit where a PMOS transistor is used as pull up, and also in CMOS a PMOS transistor is used as pull up. And we have seen except for CMOS where the low level is strong, for all the other cases we have seen the low level is weak, and as a consequence the noise margin will be poorer. That means the noise margin low, NML will be weak, poor for all these inverter configurations. On the other hand, we find that only for NMOS enhancement transistor the high level is weak, for all other cases high level is strong. So, noise margin for NMOS enhancement type pull up device is inferior, and as a consequence NMOS enhancement type transistor is never used in realizing inverters and other types of circuits. So, but we find that in terms of all these features, noise margin it is good for CMOS, power dissipation is also low, and also the low and high levels are strong. As a consequence the CMOS is the choice of present day VLSI circuits, and that is the technology that is used for realizing present day MOS circuits, VLSI circuits. So, henceforth we shall continue our discussion primarily on CMOS, and we shall see in this lecture how different types of gates, particularly NAND and NOR gates, can be realized by extending the basic concept of CMOS inverter. And we shall see that means whenever we are making it NAND or NOR gate, essentially we are increasing fan in. I shall elaborate about it, what is fan in and how the transfer characteristic is affected by fan in, that we shall discuss in detail. Then I shall also see, we shall also discuss about the impact of fan in on the noise margin, because fan in affects the noise margin, that we shall see. Then how switching characteristic is affected by fan in and fan out, that also we shall discuss. Finally, we shall end our lecture by comparing NAND and NOR gate realizations. They are compared their various characteristics. First, let us focus on fan in and fan out. So, let us consider what is fan in. Fan in. Fan is essentially the number of inputs that can be applied to a gate without affecting its operation. That means, it should behave like a gate switching device, you know that it should produce high level output, low level output, and the fan is essentially the number of inputs. So, let us consider different types of gates. First, let us consider NAND gate. NAND gate, NAND 2, where we have got 2 inputs. So, here fan in is 2. So, NAND 2 fan in is 2. Then we can have 4 input NAND gate, NAND 4, where the number of inputs is 1, 2, 3, 4, and you can have NAND 4 fan in is equal to 4. You can also have say NAND 6, where the number of inputs is 6, 1, 2, 3, 4, 5 and 6. So, here for NAND 6 fan in is 6. So, I can see we can fan in is essentially the number of inputs. Similarly, we can have NOR gates, 2 input NOR gate, NOT 2, NOT 2 again we will have fan in of 2, NOR 4 we will have fan in of 4, 4 input NOR gate, we will have fan in of 4. Similarly, you can have say NOR 6, 1, 2, 3, 4, 5, 6. So, NOR 6 and NOR 6 will have fan in of 6. So, not only NAND and NOR gates are used, other types of gates are also there, for example, AND gate, OR gate, exclusive OR gate. So, these gates are also used and which are considered to be part of the standard cell library, but we are discussing the characteristics of NAND and NOR gates primarily because it is very natural to realize NAND and NOR gates by using MOS technology. The other gates can be realized using NAND and NOR gates, later on we shall discuss about that. So, here is the concept of fan in. Now, let us consider the concept of fan out. What do we really mean by fan out? So, fan out is essentially the number of gates a particular gate is driving. For example, this inverter may be driving several gates, say it can drive only one gate, it is going to one input of an OR gate. So, in this case fan out is equal to is 1, or it can drive more than one gate, say it is driving an inverter as well as it is driving one NAND gate. So, in this case the fan out is equal to 2. Similarly, it can drive a several gates, for example, an inverter, a NAND gate, or it can drive a NOR gate and different types of gates. So, fan out in general, fan out in this particular case 1, 2, 3. So, fan out is equal to 3. So, if it goes to other more number of gates, fan out will be more. So, whenever we add more and more gates at the output of a particular gate, we have to see that performance of the circuit is not degraded and also the correct output is produced. So, that will be our study how fan in and fan out affects a particular circuit. For example, when we are extending the basic concept of inverter, an inverter can be considered as a fan out, fan in, having fan in is equal to 1. So, inverter is essentially a gate having fan in is equal to 1, but other types of gates with 2 input, 3 input or 4 input have fan in of more than 1, and how whenever you add more number of inputs, how the circuit's behavior is changing, that we shall discuss in terms of transfer characteristics, switching characteristics, noise margin and so on. So, after discussing fan in and fan out, let us consider a basic realization of a NOR gate or NAND gate. Let us start with NAND gate. NAND gate. So, a NAND function, let us consider 2 input NAND function, NAND 2. So, it has got, let us assume 2 inputs A and B, and it produces a output V, or we can say V is produces V out. As you know, for 2 inputs there are 4 possible combinations that you can apply to the gate, 1 0 0 0 1 1 0 1 1, and sorry, in this case the output for NAND gate will be whenever both of them are 1, only then it is 0, for all other cases it is 1. This is how it can be realized. Now, how you can realize a NAND 2 gate? NAND 2 gates can be very easily realized by having 2 NMOS transistors in series and connecting it to ground, because as you know, the role of the NMOS transistor network is to pull down the output to low level, and when in this particular case is pulling down, when both of them are 1, as you can see, when both of them are 1, the CL can be pulled down. Now, what is the role of the PMOS transistor? Is to produce 1, that means role of NMOS network is to produce 0, and the role of the PMOS network is to produce 1. So, you can see here the 1 is produced when any of the input is 0. So, that can be realized by having 2 PMOS transistor in parallel. So, whenever any of them is 0 as per this, then this VDD will be connected to this, applied to this load resistance, and it will be charged to high level. So, it will become 1. So, this is how you can realize a 2 input NAND gate, and in this way you can extend this concept to realize say n input NAND gate. So, an n input NAND gate will have n PMOS transistors in parallel and n NMOS transistors in series, as you can see here. So, this is connected to ground, this is connected to VDD. So, you can say this is input 1, this is input 2, this is input n, similarly this is input 1, this is input 2, this is input n, and output is taken from here, V output. So, this is the general structure of a n input NAND gate, where we have got n PMOS transistors in parallel connected to VDD and n NMOS transistors in series which is connected to ground. So, this is how you can realize a n input NAND gate. And similarly, you can have n input NOR gate realization. So, you can also realize n input NAND gate, but before NOR gate, but before we do that, we shall study the characteristics of this n input NAND gate. That means, whenever you add more than one input, that means whenever it is become multi input means input is 2, 3, 4, then how the transfer characteristic is affected, that we shall discuss. So, so here as you can see, there are n transistors in parallel, here n transistors in series. Now, this can be simplified, you can consider it as if all the n
PMOS transistors are tied together, gates are tied together, and it is represented by a single PMOS transistor. Similarly, all the gates are of the NMOS transistors are tied together, and it is represented by a single NMOS transistor, and then you have connected it to V in, and here it produces V out. How the L by W ratio is affected, I mean is changed whenever you convert it into a single inverter by tying all the inputs together, that means 1 to n all are tied together, and then it behaves as if it is an inverter. So, in that case we shall see how the transfer characteristic is affected. So, here as you can see, since n PMOS transistors in parallel, as if n resistors are in parallel, and so they are or you can say that the that W, their widths are tied together, are parallel, and so the W by L ratio will be N W P and L P. Similarly, L by W ratio of this particular transistor will be equal to that W n will not change, but the length will change, because you can see these are in series, as if you have connected n series n transistors in series. So, their lengths are tied together to form n L n, they are in series. So, L by W by L ratio for this particular inverter, which are essentially realized by tying all the inputs together, we get this. Now, what is the expression for that switching point, inverter switching point? We know that inverter switching point or inverter threshold voltage, in that particular case, what is the expression for that? VSP switching point of inverter. We know that expression is VDD plus VTP, where VTP is the threshold voltage of the PMOS transistor, plus VTN by N root beta n by beta p by 1 plus 1 by in particular for inverter this n will not be there. So, it will be 1 plus root beta n by beta p. So, we find this is the case of an for a simple inverter, where you have got only one NMOS transistor, PMOS transistor, and one NMOS transistor. But in this case, in case of a n input NAND gate, we have connected n transistors in parallel for the PMOS network and n transistors in series. How they are beta n by beta p is affected? We have already seen they are the ratio will be affected in this way: N W P L P, the width of the PMOS transistor is increased and length of the NMOS transistor is increased. So, this if we substitute, then for the switching point, V inverter switching point will be equal to VDD plus VTP. This part is not affected, but beta n by beta p, beta n by, it will be beta p, beta n by beta p, that ratio is affected. And since the length of this W by L in this particular case, it is in the denominator L, that L is increased, and here W is increased, W p is increased, and as a consequence it will be equal to V T n root 1 by n square beta n and beta p, that corresponds to an inverter. Similarly, here it will be 1 plus root 1 by n square into beta n by beta p. So, if we simplify, this will be equal to VDD plus VTP plus VTN by n root beta n by beta p and at the denominator it will have 1 plus 1 by n root beta n by beta p. Now, if we plot this is not this is the case not for inverter, for NAND gate, for n input NAND gate. So, this is VSP NAND, that was the case for inverter. How it is affected? So, if the switching point of if we consider the switching point of an inverter, in what direction it will go. So, let me plot the transfer characteristic here. So, this is the transfer characteristic. Let us assume this is your V out and this is V in, and let us assume this is the transfer characteristic for inverter. And here as you can see, this value as n increases in the denominator, this is 1 by n beta n by beta p into 1 by n. So, the value of the denominator will increase, and as a consequence this will move in this direction. So, for higher n, as increases, the switching point will move towards right, towards VDD. So, later on we shall see how much it is increased for different values of n, but for the time being we can say that for a NAND gate, the switching point moves toward VDD. Whatever is the inverter switching point, from that NAND switching point, NAND gate switching point will move towards right. So, this will indeed affect the noise margin, because ideally it should be at VDD by 2, but if it moves towards right, then the noise margin of high level will degrade, and if it moves in the left direction, the noise margin of the low level noise margin will be affected. But for the time being, we find that for NAND gate, n as n is improved, the inversion point moves towards right, and as a consequence the noise margin will be affected. Okay. Now, let us consider a NOR gate in a similar manner. So, a NOR gate, what is the realization? By extending the same concept of NAND gate, a NOR gate, as you know, if we really show the function, if it has got two inputs. So, 0 0 0 1 1 0 and 1 1, and V out for NOR gate. When it will be 1? It will be 1 for as you know, for OR gate, for these three output is 1. So, in this case this will be 0, and only for 0 0 output will be 1. That will be the case for NOR gate. So, how that can be realized? So, when both of them are 0, then output is 1. So, that means what you have to do, we have to put two PMOS transistor in series. So, when both of them are 0, then this path is closed. So, we shall get 1 at the output. And what about the NAND gate network? As you can see, when any of them, any of the input is 1, then output is 0. So, that can be very easily implemented by having two NMOS transistors in parallel and connecting the source of them to ground. So, this is here it is A and here it is B. So, this is how a 2 input NOR gate can be realized, and the idea can be extended to realize a n input NOR gate. So, an n input NOR gate will be having n PMOS transistor in series. So, 1, 2, n, and n NMOS transistors in parallel in this case. So, 1, 2, n. So, n NMOS transistors in parallel, and the source, the common, all the source points will be connected to ground, and the that series connected PMOS transistor is connected to VDD. This is how an n input NOR gate is realized. Now, in this particular case, what is the value of this V switching point NOR for a n input NOR gate? In this particular case, we find that this the value of the transconductance ratio, that beta n by beta p is equal to that transconductance ratio is equal to n square beta n by beta p, because in this particular case, as if n NMOS PMOS transistors in series, that means their width will be in series, that means their length will increase for the PMOS transistor and width of the NMOS transistor will increase, and that is the reason why it is n square beta n by beta p. So, the V switching point for the inverter will be equal to V T n plus V T p, this part remaining same. Here it will be n root beta n by beta p, and in the denominator it will have V T n plus V T p plus n root, sorry, it will be 1 plus n root beta n by beta p. So, if you plot this, what we find that the denominator value, since n is here, as n increases the denominator value increases. So, for an inverter, if the transfer characteristic is somewhat like this is for an inverter. For NOR gate, it will move towards left, because in the denominator value is increasing and this part is actually will be smaller than this. So, it will move towards, as n increases, the inverter switching point will move towards left. Okay. Now, let us consider the noise margin of the for the two cases. Noise margin. How noise margin is affected? As we know, ideally the transfer characteristic should be like this. The switching point is at VDD by 2 and this is VDD and this is your V out. Earlier by wrongly I have written V out, it will V in. So, V in against V output plot is done, and the if the switching is done in the middle, then noise margin low will be equal to noise margin high is equal to VDD by 2. But if it moves towards right, then the noise margin high will decrease. If it moves, if the switching point moves towards left, then the noise margin low will decrease. Now, let us find out the value of the switching point for different values of n and other parameters. Let us assume VDD is equal to 5 volt, then VTN is equal to absolute value of VTP is equal to 1 volt, because VTP will be equal to -1. So, we have taken the absolute value, and also let us assume WP is equal to WN is equal to LP is equal to LN. So, here we are assuming the width and length all are same. In such a case, for fan in is equal to 1, that is the case of inverter. That means, this is the case of an inverter. What is the switching point? The switching point will be equal to 2.10 volt, 2.10 volt for the inverter switching point. So, how you are getting it? Actually, V switching point inverter, as you know, is equal to VDD plus VTP plus root of beta n by beta p into V T n by 1 plus root beta n by beta p. So, in this particular case what will happen, this VTP VDD is 5, VTP is 1. So, VDD minus VTP, that will be 1, this will be equal to 5 minus 1 plus 1 plus root beta n by beta p will be equal to 3 by 1, and similarly this will be also equal to 1 plus root 3. So, if you simplify it, you will get 2.10. Now, whenever we are concerning inverter, there is no difference between NAND gate and NOR gate, these are essentially same. Now, let us consider fan in of 2. In that case, for NAND gate, as we know, it will move towards right for NOR gate, for NAND gate, and for NOR gate it will move towards left. So, this becomes 2.60 volt, it is moving towards right, it is increasing. On the other hand, it will be 1.67 for NOR gate. So, we can see it is decreasing, this is increasing. For 3 input NAND and NOR gate, the corresponding values are 2.90 and 1.48, and for 4 input the value will be 3.09 and 1.38. So, what we are observing is that since it is starting with lower value than the midpoint, by increasing it, it is becoming closer to the midpoint, then of course, it is increasing. But noise margin is definitely better for NAND gate than NOR gate, because in this particular case we see the low, that NML noise margin low is very bad. I mean instead of 2.5 it is 1.38, but here it is not that much affected, it is affected definitely, but you can see whenever the fan in is 2 or 3, then it is very close to the middle, there is small difference. So, noise margin low or high is not affected much. So, in other words, the noise margin of a NAND gate is less affected than the noise margin of a NOR gate whenever you increase the fan in. Okay. So, with this conclusion in mind, let us now move to discuss about the switching characteristics. So, whenever we consider the switching characteristics, the figure shows n pull-up PMOS transistors with their gates tied together along with a load capacitance CL. So, for the sake of simplicity, what we have assumed, as if all the NOR gates are tied together, PMOS transistors are tied together, that is the typical NAND configuration, and this is connected to CL. So, in this particular case, the equivalent circuit for NAND gate will be PMOS network for NAND gate, n input NAND gate will be as if RP and there is a switch and a capacitor, that is your C out P, and we have such n such transistors. So, RP a switch representing the transistor, depending on on or off, the switch will be closed or not closed, and again you have got C out P, these are tied together, and in this way there will be n such resistors and capacitors which are in parallel, and for the so far as the resistor is concerned, they are in series with the resistor, I mean a switch is there in series and capacitor is connected, and this is connected to the load capacitance CL. So, considering this, the TDR rise time, time delay rise time will be equal to, it can be derived Rn Rp, this is your Rp, it is charging through Rp, this is connected to VDD. So, it will charge to Rp. So, rise time will be dependent on Rp C output. So, it can be derived, that is equal to Rp by n into n C out P plus Rp by n CL. So, we find that it has got two components, and the first component is essentially for charging different output capacitances, and the second term is essentially to charge the load capacitance. And this particular derivation you will find in this reference, CMOS circuit design, layout and simulation by Baker, Lee and Boyce, published by Prentice Hall of India. In this reference you will get these details. So, this is the case for charging the capacitor. So, TDR. What about the TDF, fall time? So, to do that, what we can say that as if n transistors are in series. So, we can say that this is your load connected, then we have got n transistors in series. So, and gate is the input is connected here, and another transistor again input is connected here. So, in this way you have got n MOS transistors in series. So, representing R n, these capacitors are C out n, C out n, C out n minus 1, and finally, you will be having another resistor and a capacitor, C out 1 R n, and a capacitor connected here. This is connected to ground. So, these inputs are tied together, and here you are applying V in, and this is your load capacitance. So, the discharging take place through this path, and input is applied through these capacitances. As you know, you are applying it to the gate, and that is being represented by C in n minus 1, and this is C in n, and this is C in 1. So, it is applied to the gate, and these are the capacitances of the gate which is represented, and these are the output capacitances. And the expression for TDF will be equal to n R n C out n by n plus C load. These are essentially to charge the load capacitance and the output capacitances which are in series. Since they are in series, that is the capacitance value, equivalent capacitance is C out n by n. And another term will be there, that is for charging these input capacitances. So, this value is 0.35 R n C in n and n minus 1 square. Okay. So, these are this is the expression, again this has been taken from this reference CMOS circuit design. So, the rise time and fall time can be represented by these expressions. Now, when the value of CL is large, then other factors can be neglected. So, TDR will become equal to this part RP by N into CL, and of course, in the worst case when only one transistor is on, remaining transistors is off, this will be equal to RP into CL. Similarly, the TDF will be equal to N R N C load. The other factors can be neglected when N is very large. Okay. Now, let us focus on the NOR gate. In a similar way, we can derive expressions for NOR gate, and this is the summary of the switching characteristics of the NAND and NOR gates. So, TDR for NAND gate is equal to RP by N into N C out P plus C out N by N plus C load. So, here not only output capacitance, I mean for the PMOS transistors, output capacitance of the NMOS transistors has also been taken into consideration. So, we find that as the fan is increased, this rise time will also increase. However, worst case rise time will be equal to RP into C out P plus C out N plus CL only when one transistor is on. That means, although N PMOS transistors are in parallel, only in the worst case
the delay, the rise time will be maximum only when one of them is on. Similarly, the fault time is n R n into C out n by n plus n C out p plus C L. And again in this case, when the and also that expression for charging the input capacitance is given here. This is the expression, and when C L is large, the TDF is equal to n R n C L and TDR is equal to R P C L. So, here we find that the fault time for the NAND gate is affected and it increases linearly with the value of n for large and the rise time is not affected much. It is very similar to that of an inverter. Similarly, for the NOR gate, we find that TDF is equal to R n by n into n C out p plus C L. In this case, p n PMOS transistor are in series. That is the reason why the fault time will not be affected much, and for n is equal to 1, I mean when one of the transistors is on, then it will be equal to RNCL as you can see. However, the rise time will be affected with the value of n. So, TDR is equal to n RPCL. So, for large CL load capacitance, it will be proportional to the fan out is affected by the the for delay, that DDR will be affected by the number of inputs. So, n RP CL. So, this is how the delay times are affected because of fan in is demonstrated. Not only fan in, but also it shows it is proportional to CL. That means, the delay characteristics, switching characteristics is affected not only by fan in, but also by the fan out or load capacitance. You see, whenever the fan out is increased, essentially the load capacitance increases. So, here is the comparison of different parameters. We find that the area increases linearly with increase in fan in for both the gates, that you have already seen, because we are increasing the number of transistors. We have seen that as the fan is increased, the number of transistors is increased. For 2 input, it becomes double that of an inverter, and for n input there are n PMOS and n NMOS transistors. So, area increases linearly as the value of n increases. What about noise margin? For equal fan in, noise margin is better for NAND gates compared to NOR gates, that you have already seen how the noise margin is affected based on this particular table. Particularly, we find that the noise margin is good, is better for NAND gate compared to NOR gate for equal area. So, in that particular case, we considered minimum area. What about delay? Delay increases linearly with increase in fan in and fan out, and particularly for NAND gate and NOR gate, with respect to the inverter, it is proportional to n, where n is the fan in of any NAND or NOR gate, NAND or NOR gate. In addition to that, so n is the fan in, it has dependence on fan out as well, and that is the reason why the number of fan is restricted to 4. Although gates are available with fan in starting from 2 to maybe 8, but whenever you realize practical VLSI circuits of reasonable performance, then there is some restriction on the fan in. Fan in is usually restricted to 4. That means, whenever you will choose standard gates from the library, you will choose gates with fan in less than equal to 4, and you will realize multi-level circuits using gates with fan out, fan in is equal to 2 or 3 or 4, not more than 4. So, what is the conclusion? Conclusion is that for equal area design, NAND gates are faster and better alternative to NOR gates. So, this is the conclusion that we can make from the comparison of area, noise margin, delay and other parameters. So, here is the summary of different types of whatever we have discussed today. So, multi-input NAND and NOR gates are extension of basic CMOS inverter. We have discussed how the multi-input NAND and NOR gates can be realized by extending the basic concept of an inverter by adding more and more number of transistors as the fan in increases. And we have seen the transfer characteristics does not remain symmetric with fan in. So, transfer characteristic is affected with the fan in, that we have discussed in detail. Now, for the third conclusion is, for the same area NAND gates are superior to NOR in switching characteristic. Another very interesting point that we can consider, we have seen that the switching characteristics is becoming asymmetrical as the fan is increased. But if we consider say fan in is equal to 3, let us consider a NAND gate. In case of NAND gate, we know that we have 3 PMOS transistors in parallel and 3 NMOS transistors in series. Now, in this particular case, if we consider minimum size, then that means W L is equal to W n is equal to L n is equal to W p is equal to L p. So, in such a case, what will be the switching characteristics of this? Particularly the beta n by beta p ratio in this particular case will be equal to how much? As we know, since they are of the same length, say length and width, we know that for this particular configuration, beta n by beta p corresponding the equivalent beta n by beta p will be is equal to 1 by n. What is n? N is the number of inputs in this case. Now, we know that beta n by beta p, this value is also 3. In this case, n is also 3. That means, we can say this this transconductance ratio is equal to 1, because beta n by beta p is equal to 3 and n is also 3. So, this makes it 1. So, that means, for a 3 input NAND gate, the inverters the switching point will be exactly at VDD by 2, because the equivalent beta n by beta p transconductance ratio or beta n by beta p is equal to 1. We know that when this is 1, then the beta the VSP say NAND 3 will be equal to VDD by 2. The reason for that is denominator will become 1 plus 1, and also numerator will be that Tp and Tn will cancel, it will be VDD. So, it will be VDD by 2. So, we find that for this particular case it is becoming perfectly symmetric, but that will not be situation for NOR gate, and that is the reason why our conclusion is for the same area NAND gates are superior for NOR gates in switching characteristic. Particularly the fan in is the noise margin is better, and also for the same delay NAND gates require lesser area than NOR gates. We know that if we want to have the rise time and fall time identical, then the W p has to be 3 times that of W n. So, this is the requirement for equal rise and fall time. So, TDR is equal to TDF. If we want this, then this is the requirement. So, in such a case the area increases. That is the reason why we can say that for the same delay NOR gates require lesser area than NOR gates, and for the same area NAND gates are superior to NOR gates in switching characteristics. Then noise margin and switching characteristics are better for NAND gates compared to NOR gates, that we have already discussed in detail, and NAND gates are better alternative to NOR gates. From all these discussions, this is our conclusion: NOR gates are better alternative to NOR gates. So, although this is our conclusion by considering the noise margin, delay characteristics, area, NAND gates are superior, but in practice we shall be using both NAND and NOR gates together. So, you will see that whenever you will be realizing multi input, multi out, multi level gates, multi level circuits, multi level multi input circuits, then you will find that we shall be using both NAND and NOR gates, because in that case overall area, overall delay characteristics is important rather than individual area or delay characteristics. So, our conclusion is that we shall be using both NAND, NOR and other types of gates in realizing circuits, but if possible we shall choose NAND over NOR whenever it will be permitted by the realization technique. So, with this we have come to the end of today's lecture. In the next lecture we shall continue our discussion on the same topic, that is your static CMOS circuits, and we shall consider how we can realize other types of gates and more complex types of static CMOS gates. Thank you.